All right, let's go over some questions, homework questions from Unit 1, Module 4. I believe I need to take screenshots to annotate, but okay, so question one about subatomic particles. Xenon is one of the large noble gases and has several isotopes. Okay, xenon 133 is one of the radioactive isotopes. How many protons, neutrons, and electrons does xenon 133 possess? Okay, so xenon. Oh, I can annotate. Anyway, so xenon is, we need to go to the periodic table first to see, to determine the atomic number of xenon. So if you go to a periodic table, the atomic number of xenon is 54. Okay, that's the whole number you find for xenon. So the atomic number is 54, meaning it has 54 protons. And then if we have a mass number of 133, that means we have the neutrons plus protons is 133. Okay, if neutrons plus protons is 133 and number of protons is 54, because it's not going to change. It determines the identity of the element, right? Then n plus number of neutrons plus 54 is 133. Therefore, number of neutrons is 133 minus 54. Okay, and then that's going to give us 46, 76, 79 neutrons. So it has 79 neutrons. Okay, and then we are talking about the neutral atom, the neutral xenon atoms. It's going to have the same number of electrons as the number of protons, because they have the charges are equal in magnitude and opposite in sign. Okay, therefore we should have 54 electrons as well. So that answer seems to be option D. So 54 protons, 79 neutrons, and 54 electrons. Therefore, the correct answer here is option D. Okay, moving on to the next question. Again, let's do it. Right, identify the number of each type of subatomic particles present in the ion gallium 3+. Okay, so remember the number on the top left corner is the mass number, meaning number of protons plus neutrons, right? So number of protons plus neutrons is 70. And gallium, the atomic number, if you go to the periodic table and locate Ga, atomic symbol Ga, you see that it has 31, and the atomic number of that is 31, meaning it has 31 protons. Okay, so protons should be 31. How do we get it? The atomic number from the periodic table. And because number of protons plus neutrons is 70, the number of neutrons must be 70 minus 31. So that should be 39 neutrons. And then the neutral atom, neutral gallium, should have 31 electrons as well. But because we're talking about gallium 3+, it has 3 less electrons than the number of protons, and that should be 28. So the number of electrons should be 28. 3 less electrons than the number of protons. Okay, so that answer is not this, and it must be not this. It should have less protons. Therefore, it should be option D again. All right, moving on to the next question. Yep, this is the mass spectrum of Br2 based on the data. How many isotopes of Br exist in nature? It's an easy one, but to the annotation still. So this is Br2, right? So the mass of the entire molecule is given by the rightmost peak. So the peaks correspond to the highest mass, which are these guys. Okay. Now we see we have two other peaks around 80 over here, right? Meaning we have, so how do we get the peaks at 80? By breaking the molecule. So how do we break a Br2 molecule? Right, the only possibility is breaking the molecule from this bond, right? And that's how we end up with peaks around 80. So I see two peaks there, meaning there should be atoms with two different masses for Br, meaning there should be two isotopes. Okay, there should be two isotopes. So now I want to mention one other thing here. So let's analyze it a little bit more while we are on this problem. Okay, so now what are the masses of this? Okay, so we see that one is little bit one isotope is a little bit less than 80, and the other one is a little bit more than 80. Okay, so and then how do these combine? So let's call this 81 and this is 79. All right, let's see how we get these Br2 peaks in this area in the mass spectrum. Okay, with this. So for a moment, let's assume that 281 bromine 81 atoms combine. Okay, if they combine, then that Br2, okay, so 81 here and 81 here should have a mass of 162. Okay, that seems like this peak over here, 162. Okay, that's one. And then let me erase this again. And the other possibility is we can combine two lighter atoms of Br, isotopes of Br. That means 79 plus 79. So if you combine 279 atoms, what do we get? We should get 158. Okay, so is that right? Yeah, I hope so. Okay, so we should, that's how we get 158. How do we get 158 peak? By having a combination of two light atoms. Not combination, by combining two light atoms to make Br2. And what about the peak at 160 then? All right, so let's do that again. The other possibility, only other possibility is a lighter atom combines with a heavier atom, 81. So 81 plus 79, what do we get? We get 160. Yeah, so okay, and that's how we get these peaks. Just to interpret this mass spectrum. Let's do one or maybe two other questions, and this should be enough. Let's see. The mass spectrum of an unknown substance is shown below. What is the likely molar mass of this compound? Again, the molar mass is given by the rightmost peak. Remember, it's not about the height, it's about the mass. Okay, so the highest mass is the peak that corresponds to the highest mass is around 30. So I'm going to go with 30 for that. So that should, that should be the answer for that. And then that was easy. And molecular formula. All right, so you're given the mass spectrum of something. Based on the mass spectrum, what is the most likely molecular formula of the substance? Okay, you know what? Let's do this really quickly. All right, now, now we do not want to overcomplicate a question like this. All right, so we know we can get the molar mass of the entire molecule from the mass spectrum, and that is given by this peak over here, which is also known as the molecular ion peak, or the peak that corresponds to the highest mass, right? And it seems like, so this is 20, 30, 40, 50. So this is between 30 and 40. So I'm going to call it 135 as the molar mass of this compound. Okay. So what we want to do is we want to see which one of these has a mass of 135. That's all we need to do. Okay, and how do we do that? First one, we have carbon, which is 12, and hydrogen, which is 1, and then 3 fluorines, which is 19, I believe. If you go to fluorine, in the periodic table, you see the relative atomic mass. The average relative atomic mass is 18.998, right? We'll call it 19 for the moment, and let's see how it goes. So we have 3 times 19, it should be 57. 57 plus 1 is 58. 58 plus 12 is 70. Yes, call it 70. Yeah, 70, which is less than 135. Therefore, this is not it. And the next one, we have 3 carbons, 3 times 12, plus 3 hydrogens, 3 times 1, plus 5 fluorines. Seems to be pretty heavy. Okay, so okay, so 5 times 19 is 95. Yeah, 100. So this is 95. 95 plus 3 is 98. 98 plus 36. Okay, so this is gonna add up to 98 plus 36, which should be 134, which is pretty close to this. Right now, this seems to be the best candidate, so we'll come back to it. Okay, and the next one, we have 1 carbon, that is 12, plus 1 fluorine, that is 35.45, it's called 5, and then 3 fluorines, which is 3 times 19. See, so decimal place, this is 3 times. Okay, anyway, so this should be 57 plus 35.5 is 87, 92.5. 92.5 plus 12 is 204.5, I think. You should check your math. 104.5, which is not 135, therefore this is not it. And lastly, we have 12 plus 2, it's not 3, it is 2. 2 times 35.5, 2 chlorines, and then 2 times 19 for the fluorines. Okay, if you add this up, you're gonna get 38 plus 71. Let's do this. 12 plus 71 plus 38. All right, and then if you add this up, this will add up to 109, 100 and it's going to be 121. Yeah, something close to that, right? 30 is 100, 100, 909. Yeah, so I think it should be 121 or something like that, which is not 135. Okay, so this is the closest to our answer. So I'm going to go B as our answer for this question. I want to leave some of these for your entertainment purposes. I mean, when you discover things yourself, I mean, it gives you some happiness. Maybe I can do this one. Okay, let's see what's going on here. All right, the mass spectrum of a compound acetone is given below. What is the likely chemical composition of the ion that generates the tallest peak in the spectrum? Okay, so acetone, okay, is this much, and the tallest peak is over here, and that has a mass of what? Give me a second. Now 1, 2, 3, 4, 5. So this should be 41. Oh, yeah, it should be 42, 4, 6, 8. Okay, it should be 42, 43. I want to say this is at 43. Okay, so all we basically need. Okay, we can think about what is lost and stuff like that, but we don't care about that. So, but we know the tallest peak is at 43. What's the significance of this peak? This corresponds to the fragment that is most stable under the harsh mass spectrometric conditions. That's it. Okay, it doesn't tell us anything else. All right, anyway, so first fragment over here has a mass of 15, carbon is 12, hydrogen is 1, 3 of them is 3, 3 plus 12 is 15. That is not it. Okay, this is not it. And then C3H6O is this, the entire thing. I mean, you know, it's the entire molecule. So that cannot be. I mean, you know, it's not a fragment, it's the entire molecule. Which has definitely a mass greater than 43. I'll show you if you want to. 3 times 12 is 36, plus 6 is 42. 42 plus 16 for oxygen is 58. Yeah, some 58. This is much larger than 43. All right, anyway, that's not it. And then I mean, I like C, but let's come back to C. So option D is easy. 12 plus 16 is 28, because carbon is 12, oxygen is 16. That should be 28. So that's not it. Therefore, this should be our answer, but we can verify that as well. What has happened is we have lost a CH3 group or something like that. Okay, so I think we have broken the molecule from over here. So if you, let's say we broke the molecule from over here, we have this part, and then we have this part. This should be 15, and then 58 minus 15 should be 43. Okay, we can verify it. So we, you know, that's a different story. All we have to do is to determine the masses of these fragments. So 2 times 12 for the 2 carbons, plus 3 times 1 for the 3 hydrogens, plus 16. I bet this is going to give us 43. 2 times 12 is 24. 24 plus 3 is 27. 27 plus 16 is, guess what? 43. So this should be your answer. All right, I think rest of these are pretty straightforward, I believe. I mean, you know what? Sake of it, they can do this as well when we're looking at it. Some of the formulas below could be either empirical or molecular formulas. Nevertheless, some of them can only be a molecular formula. Okay, which of them must be a molecular formula? Must be molecular formulas, and select all that up by. All right. Now, if it is an empirical formula, okay, you should have the lowest whole number ratio between the atoms. For an example, the first one, CH. I mean, you cannot divide that further. That must be an empirical formula. Can it be a molecular formula? It's unlikely, but let's say, okay. But it's an empirical formula. But they're asking for must be molecular formulas. Which of them must be molecular formulas? Okay. So we know C2H6 is not an empirical formula. So it must be a molecular formula. Wow. Okay, because C2 and 2 and 6 can be simplified further into 1 and 3. Therefore, it's not an empirical formula. Therefore, this must be a molecular formula. C2H6O can be either, right? So it can be an empirical formula because the ratio here is 2 to 6 to 1. We cannot simplify it further. So it can be an empirical formula. Or also it can be not O, and it can be a molecular formula. Okay, so it's both possible. Okay, therefore this is not, I'm not going to select that. And then option D, on the other hand, we have 393. The ratio is 393. This is not the lowest whole number ratio. This can be further simplified into 1, 3, and 1. Okay, therefore this must be a molecular formula. So I'm going to select options B and D as the answer for this. Okay. All right, so with that, only three more questions. So quickly, let's see what's going on here. The elemental analysis of a substance is this. Based on the elemental analysis, what is the empirical formula? Okay. Oh yeah, you know what? Let's do that as well. Not okay. So I think the best way to do this is we take a certain amount of this substance and determine the moles of carbon, in this case carbon, hydrogen, and oxygen in it. That's it. That's all we do. So let's take 100 grams of this substance. Okay. And if you take 100 grams, carbon, the mass of carbon would be 55.8 grams. And the mass of hydrogen must be 7.03 grams. And the mass of oxygen must be 37.17 grams. Okay, because percentage means per 100. Per 100 grams, 55.8 grams should be carbon and so forth. That's what it says. All right. Now, once we have that, these are the masses. And we can determine the moles we have in them. 55.8 grams. If you want to determine the moles of carbon, I'm going to divide this by the molar mass of carbon, which is 12 grams per mole. And then to determine the moles of hydrogen, I'm going to divide 7.03 grams by molar mass of hydrogen, which is 1 gram per mole. And then to determine the moles of oxygen, I'm going to divide 37.17 grams by the molar mass of oxygen, which is 16 grams per mole. Okay, so in this case, grams cancel out. We're going to end up with moles. So let's determine that values. So 55.8 divided by 12 is 4.65. So we get 4.65 moles here, and then 7 moles here. And then for oxygen, it should be 2 point something. Let's see. We have 37.17 divided by 16, which is 2.323. 2.32 moles. Okay. And now to get the lowest whole number ratio, we want to divide everything by the smallest number. Okay. So if we want to do that, what we can do, let me see if I can change the color. So the smallest number here is 2.32. So if I divide 2.32 by 2.32, we are going to get 1 mole here, and then this divided by 2.32, and this divided by 2.32. This seems like 2 moles. Okay, and then 7 divided by 2.32, I believe it is 3 moles. Yeah, this is the lowest whole number ratio. So 2 carbons, 3 hydrogens, and 1 oxygen. So therefore, that should be your empirical formula, which is option B. Okay, there are 2 more questions. Yeah, but you know what? I'm gonna do this one as well. Maybe one last question. Why not? All right. The elemental analysis of a substance is given here, and also the mass spectrum is given here. You also determine the molecular formula, and then we talked about this in class as well, right? So based on the mass spectrum, from the mass spectrum, we determine the molar mass of the compound. The molar mass is This is 1, 2, 3, 4, 5. We can call it 64 or 65. Okay. So yeah, it doesn't matter. So let's call it 65. Yeah. So I'm going to pick 1, 2, 3, 4, 5. This peak over here. I mean, so it might be an isotope. All right. So molar mass peak might be the peak just before that, but I'm going to show you it should not matter that much. All right. So let's see. So the entire molecule has a mass of, let me see if I can change the thickness here. Okay. Anyway, has a mass of 65 grams. Okay. So out of that 65 grams, okay, per mole, okay, if you take 1 mole of this, in other words, out of the 65, 37.51, okay, 37.51% per 100 is the mass of carbon. So this is the mass of carbon, okay? And if you divide this by the molar mass of carbon, which is 12 grams per mole, you're going to get the number of moles in 1 mole of this compound. Okay, I'm going to write out the, I'm going to set up everything first and then use the calculator. Let's think about hydrogen now. 65 is the entire molecule, entire mass. And then out of that, 3.15, let's put it over here, 3.15 per 100 is the mass of hydrogen, and then divide this by the molar mass of hydrogen, which is 1 gram per mole. Okay, you're gonna get the moles of hydrogen. And lastly, we have fluorine, not oxygen, fluorine, fluorine in it. So out of 65 grams, 59, a lot of that, 59.34% is the mass of fluorine. Divide that by the molar mass of fluorine, which is around 19 grams per mole. You're going to get the moles of fluorine. All right, so now let's plug and chuck these numbers into a calculator and determine the moles. Yeah, why don't we do it here? Okay, so for carbon, we have 65 and then multiplied by, we can multiply by 0.3751, or maybe you can do, yes, because 37.51 divided by 100 is 0.3751. I'm going to do that. Multiply by 0.33751 and then divide this by 12. I get around 2. Value is around 2 moles. This is in moles because grams cancel out. Moles go up to the numerator, therefore it should be 2 moles. Okay. And when it comes to hydrogen, it should be 0.315 divided by 1 now. Okay. Oh, it's again 2.0475. Okay. I'm going to call it 2 moles. And then when it comes to fluorine, see what we have, 5934. 5934. Oh, wow, that also gave me 2.03. So that is also around 2 moles. So without thinking too much, what it tells us is if you take 1 mole of this compound, it has 2 moles of carbon, 2 moles of hydrogen, and then 2 moles of fluorine. Okay, and this should be the molecular formula, and that looks like option D. That's it. All right, now that is that. Only one question is remaining. So it's a similar question. You are given the mass spectrum, okay, and then the elemental analysis as well. Chemical composition means the elemental analysis, okay, and then you are asked to find the molecular formula. You do the same thing as we did before. Yeah. So 60, I would say 70, 80, 90. So it should be the molar mass is around 170. Oh, there's another way of doing this, by the way. I'll show you a shortcut, okay? So basically, I did the entire thing. Anyway, so another way of doing the same thing is, you see that the molar mass is 170. Okay. Now, I can eliminate 170 grams more, right? So I can eliminate some of these options because the molar mass do not match. For an example, if you take option A, I might not do the entire thing here. So molar mass of option A is 12 for carbon, and 2 chlorines is 2 times 35.5, right? So 35.5 times 2 is 71. 71 plus 12 is 83. 71. 83, right? Yeah, it's 83, which is not 170. So therefore, this is out. Okay, next one. So we have 5 times 12 plus 3 times 35.5. Okay, it's getting complicated, but anyway, that's okay. So 5 times 12 is 60. 3 times 35.5 is 106.5, I believe. 106.5. This kind, 106.5 plus 60 is 166.5. This is pretty close. Okay, this is pretty close to that, but let's check the other ones as well. Option C, 2 times 12 for 2 carbons, and then 4 times 35.5. All right, 2 times 12 is 24, and then 4 times 35.5 is 142. 142. So this should be 166. 66, which is pretty close to what we're seeing here, right? And then lastly, we have 4 carbons, 4 times 12 plus 3 times 35.5. 4 times 12 is 48. Okay, and then 3 times 35.5, if we had the correct number before, should be 106.5. Okay, if you add this up, this is going to be 156, 154, 154.5, which is pretty low. So maybe this cannot be it either. Okay, it must be between these two, between B and C. Okay, so sometimes, again, it didn't work out for this entirely, but we were able to eliminate 2 options here, okay, based on the molar mass alone. But sometimes what happens is, if you just calculate the molar mass do not match for the wrong answers, okay, so that itself should be enough. But in this case, it did not happen. So we can actually determine the percentage of chlorine here or something like that, and to determine this. For an example, so you see that the percentage of chlorine is pretty low, pretty high here, or percentage of carbon is pretty low here. Okay, so that leads me to think that this is something like C2Cl2 rather than C5Cl3. Okay, because 106 plus 60, 106 and 60 is a larger percentage. But anyway, so this is what I mean. So let's calculate the percentage of carbon in this option C. Okay, so out of 166, 24 is the mass of carbon, and you multiply that by 100, and that should give you the percentage of carbon. All right, let's do that really quickly. This is an alternative way, or you can do the same thing we did before in the previous question. Okay, so if we did this number, 24 divided by 6, all right, you see the percentage of carbon is 14.45. 14.45%. On the other hand, all right, if you calculate the percentage of carbon in option B, it's gonna be 3 times that. Okay, let me show you what I mean. So the molar mass of this compound B is 166.5. Okay, so out of 166.5, the mass of carbon is 60. This number over here. Multiply this by 100, you get the percentage of carbon. So what do we get here? Let me show you. 60, and that is 36, around 36%. Okay, so but we only have 14.49% carbon here, therefore option B is out as well. Therefore the correct answer is option C. Now you can do this. I mean, for me to do this, I follow the elimination method. The other way of doing this is like we did in the previous question. You just use the elemental analysis and the molar mass to calculate the moles of carbon and chlorine in it, and then you match that with the option. Matches with that. That's it. Yeah, all right. So I went over the entire homework because I'm actually having any need to do that, but I did it anyway. All right. I hope this helps. I'll see you guys in class. Bye, everybody.